We know, right? We know it's sweet. How was your weekend, Eunice? Yeah.
This wait, what day is today? This weekend I'm gonna go to Florida.
Florida? What you going there for?
I don't know. My parents are just fighting. Like I don't know where I'm going.
Oh, you're just going for vacation?
Yeah.
Oh, fun. For Thanksgiving break? Or
Yeah.
you're gonna have Thanksgiving dinner down there?
Yeah.
What do y'all have for Thanksgiving dinner?
Chicken stuff.
Chicken stuff? Okay.
Chicken, rice, and we just catch a chicken and like eat it live.
No, you don't.
No, like we cut it and then we eat it.
You catch a chicken?
Yeah.
Where do you do that?
At a farm.
What farm do you go to where you can catch a chicken?
Like a Buford.
Okay. A chicken, not a turkey?
No.
Interesting. A chicken barely feed your family. You'd need 2 chickens, wouldn't you?
Not really. My parents won't eat chicken, so.
Oh, they don't eat it?
And they don't eat that much. I think someone's coming.
Yeah, somebody's coming.
Yeah.
So you go and catch a chicken and then you eat it. That's craziness. That sounds like fun. Morning, boys. How goes it? You guys have plans for Thanksgiving?
No.
Nothing. No. Just chilling.
Where's your glasses? I have contacts on today.
Nice. Are those new?
No, I've had them for like 2 months maybe.
Okay. Just don't wear them very often.
Yeah.
I can't see anything without mine, so. And I much prefer them to my glasses.
Yeah, because glasses. I just need glasses. Sometimes they just fall off.
Well, my problem with my glasses is, so my vision, the way it's corrected with lenses, with glasses, is it makes everything kind of smaller. So wherever I can't see, like peripherally, I have to, like, if I'm going down the stairs, I have to look straight down because otherwise I fall. But the other weird thing that I do that I didn't realize till after I'd done it many times is because it kind of shrinks everything. It messes with my brain. So when I'm putting food on my plate, I put way too much food on my plate. And then I'm always like, why can't I eat this? But every time I'm wearing my glasses, I overserve myself because it doesn't look like enough. It's really weird. Yeah. Yeah.
I need glasses when I'm reading and watching stuff.
Yeah. Well, I can't, if
I feel like,
I used to joke,
but I can't see.
I used to joke that if I didn't paint my toenails, I couldn't tell my toes apart without my lenses in, because it was all just one big flesh colored blob. But now it's so bad you can't even tell them apart with that, you know, just forget it.
Which was all those colors.
Okay, somebody got some of them last week.
Was it Emma?
Emma got some of them, yeah.
I have no idea how to solve that.
It was pretty impressive.
Do you need help with your lab? My brother is like, he's like giving everyone answers.
I saw that. Yeah, he was. I saw that. He was throwing them out there. That's good. That's what I want y'all to do. So, yeah.
I was like,
Yeah, and for whatever reason, for certain people, it's telling them that an admin has to approve their post, but I don't have it set up so that I should have to approve posts. So I don't know why it's doing that. So I got to go in this afternoon and spend some time trying to figure out what's up with my settings on my website. Woohoo, websites are interesting. Well, I'm going to give Emma and Darcy a minute to come. Lewis has apparently got a little cold and was coffee last week, and he's continued to be coughing at a little bit today. So his mom was like, I don't think he's catchy, but I'll keep him home so he doesn't spread any germs.
Has scrambled up.
There's Miss Darcy. What's up?
Not much.
Wow,
Just wake up and having 20 minutes.
girl, you were running. 20 minutes is about the
My
length of your
dad
trip,
drove
isn't it?
like this.
Oh, well. So do y'all know any, do you guys come from, I know where he comes from, and I know where she comes from. Do you guys come from like across the river, or where do y'all live?
We live in Beacon.
Okay, so you do come across. the
Next to Second June.
Yeah, okay. Do you come,
You'll see
so do you come
this.
down 20 or do you come down McGinnis Ferry?
McGinnister.
Okay, yeah, so just so you'll know, this won't apply to you, Eunice, because you come from around the corner the other way.
I
But
told Stevie's.
There is a back road that a lot of people miss. So right at the intersection of Old Atlanta Road and McGinnis Ferry Road, sometimes it gets backed up there. Okay, so you know when you're coming down McGinnis Ferry, you see those soccer fields?
Yeah.
Okay, so where the soccer fields are, there's a road called Kemp, K-E-M-P.
Yep.
And if you take Kemp Road, it doesn't show up on Waze and stuff a lot because it's about 80% of it's a dirt road. 80% of it's a gravel road.
I used to
but
ride that. all the
There's
time.
there's a little cemetery there, historic cemetery. You pass all that, you pass like there's like a water facility of some kind there. And then the road turns from paved to gravel. And it winds through these properties with this big horse farm and all this stuff. It's really pretty. And it spits you out on Old Atlanta where that tiny little church is right before you get to the school. So it avoids that whole intersection. So sometimes it's helpful, especially if you're trying to come out of here and go the other, like go home, to go left on McGinnis Ferry.
I was in St. Marlowe. We used to take that road.
I bet, yeah.
And like we used to walk our dogs, we used to ride bikes along it.
Yeah.
You just gotta be careful when you're driving because sometimes a car will come really fast.
Yeah.
So it's just like watch.
It's a nice little road. Yeah.
Oh, and there are cats like cross there.
Yeah. There's a lot of deer too back there.
I'm gonna turn in my brother's lap.
Yes, you do that, and I'll let you do that real quick, and then we'll go ahead and start. But or actually, you can hand it to me so you don't have to run off the pass.
This is mine. That's why it's folded
It's a
up. like
beautiful
that.
shape. I love the reverence with which you treated your lab.
I couldn't fit it in my bag and I was panicked.
Great.
What?
All right. Let me see. Does anybody wish to claim this cool Rico?
Oh, that's mine.
Yeah, good job. All right, awesome.
Liking.
I like him.
Even did my lesson 13 on Tuesday.
Look at you.
No.
All right, so we are going to do work, power, and machines continued. So guys, remember that you're paying lots of attention to all this stuff with machines. And we start talking about transfer of energy in the next couple of weeks. This is going to be the stuff that's really going to play into your Rube Goldberg final project. So for this lesson, we have a lot of rats in Victorian factories. Pretty cool. Yeah, kind of. Yeah, the sweatshops of the day. So let's talk about mechanical advantage and efficiency. All right, so machines do work. A machine is a device that changes what? What do we say? All right, Eunice, do you know? It does work by changing, do you know? Oh, Darcy?
Is there?
It changes. Force.
Yes, the changes of force. Okay. So machines make work easier to do. They change the size of the force or the direction of the force or the distance over which a force acts. So these are big things. They change the size, direction, or distance over which it acts. So the force you exert on a machine is what? What is it, Eunice?
Input.
That's your input. Obviously, I'm putting it in, right? So sometimes you'll see it called the effort force. And like when you're working with levers, sometimes I think your lab last week referred to your lever as having an effort arm, right? So that's the part where you're putting in the force. And then the force is exerted by the machine. And that's called what? Input goes in. What do you call it when it's
I'm pretty sure I got this one.
coming out of the machine? Yeah, output. There you go. Carlos has got it. It's an output force. Okay, so you put the force in, the machine changes it, and on its way out, we call it an output force. All right, so to calculate the amount of work a machine does, we're going to multiply what by what? All right, Darcy, you got it.
By distance.
Okay, force by the distance. All right, so we said already a machine can changes a force by either changing a distance or a direction or the size of the force. So we have what we call mechanical advantage. This is basically how useful is this machine to me? What is the advantage of using this machine? It is something like that. Looks like it has some pulleys going on. So a machine's mechanical advantage is the number of times a force exerted on a machine is multiplied by the machine. So what do we call that ratio of output force to input force? Nicholas, you want to guess? Nico's like, I don't want to guess. I'm not awake. All right, Eunice.
Mechanical advantage.
That's your mechanical advantage. Okay.
Oh,
So it's the ratio of output force to input force. So this is where you see math words in a sentence. So what does ratio mean when you're like, what's a mathematical way to describe it, Darcy?
like a fraction?
Fraction's a perfect way to describe it. A fraction. Okay, so I want you to think about this. Think about the fraction 3/4. Like picture it in your head, 3/4. Okay. If I handed it to you and I didn't say this is a fraction. I said this is a math problem. What would you do?
So,
How would you do it?
well, I mean, what are we trying to solve?
Yeah, what is 3/4?
We'll just do.
Say it louder.
3 divided by 4.
3 divided by
Just want
4.
to turn it into a mixed number?
Well, what I'm asking is 3/4.
Yeah.
It's a division problem, right? So a ratio is a fraction, basically, and then a fraction is a division problem. So what it's saying here is your mechanical advantage is the ratio of output to input. So keep that in mind, all right? We're dividing something here, right? So the number of times a machine increases an input force. So for a machine that multiplies what? The mechanical advantage is greater than 1. What do we think? What do we think, Nico?
Force.
All right, for machines that multiplies force, your mechanical advantage is going to be greater than 1 because that's what we're aiming for, right? If you're multiplying the force, that's how a machine's going to make work easier. It's going to do it by taking whatever force you put in and multiplying that force on the other end. All right, so because the output force is greater than the input. All right, so think about that for 1 second. Just think about that. If the output force is greater than the input force, and it was a division problem, and it needed to be greater than 1, which number of that division problem is going to be on the top versus which is on the bottom? So it says multiplies force, right? So if the mechanical advantage is greater than 1, the output force is greater than the input force. So the output force has the starting number of the output force has to be,
It'd be the denominator.
it's got to be on the top. Because think about it, like if you had 4/3,
That's an improper fraction.
right? But if you did the division, it's going to be greater than 1, right? Right. So because if you divide it in, it'll go into it more than 1 time. 3 will go into 4 more than 1 time. So you know that means your output force is on the top because it's greater. So that's how you remember when it says the ratio of output force to input force, you put output first or on top, input on bottom. All right. So then for a machine that multiplies what? The mechanical advantage is less than 1. Okay. Nico, you do this one too. There you go. So distance. Yeah. So if it multiplies distance, yeah, there you go. You can have that one, Darcy. All right. So for a machine that multiplies distance, the mechanical advantage is less than 1 because the output force is less than the input force. So this would mean if it's multiplying distance, whatever force you're putting in is greater than the force coming out of the machine, but the distance over which you're putting in that force is smaller than the distance in which it comes out on the other end. All right, and then we said this one, if a machine changes the direction of a force, the mechanical advantage is 1 because it's equal. All right, so this is kind of like a simple pulley. Even if you just tossed a rope around a tree and tied a rock to one end of the rope and stood next to the rock, you pull this way, the rock's going that way, right? Because it's looped around a tree. So in that situation,
Did that with a chalk
Change
box
direction.
and caught a bird.
oh,
This was
really?
This is when I was going to school in like 2nd grade. We all excited because I was like, oh, I found a bit of rope in a box. Let's catch something.
All right, there you go. There you go. Okay, so what's the number of times a machine increases an input force? Eunice?
Efficiency.
Yeah, well, okay, well, yeah, still, we're getting there. So that's mechanical advantage. And then this is, here we go, actual mechanical advantage in ideal. Okay, somebody tell me what's the difference between actual and ideal. Darcy, what is it?
The input and it's output force and input force, and then it's input distance and output distance.
Mm-hmm. What does it mean, an actual mechanical advantage versus an ideal?
And a mechanical advantage might be like a small advantage, but
Mhm.
an ideal mechanical advantage is the amount of advantage that you actually want.
Right, exactly what you want. So how come, what does it mean to be ideal? What does it mean if you say something's ideal? Like this is an ideal vacation. It's like a
To our liking.
to your liking. That's a good way to put it. I'd say it probably means perfect, like real close to perfect, right?
It's ideal to.
Yes, it's my ideal job. This is perfect. But when you use the word ideal, it kind of implies that it's
Ideal is like.
it's like, but it's kind of like something that's perfect but can't really be perfect. Like think about it. Is there really such a thing as truly ideal job or a truly ideal house? It's always something that's a little like, well, this is an ideal house, except the location's a little weird, or but you have to kind of think of it like that. So why can't you ever really have an ideal mechanical advantage? How come that's not what actually happens?
Perfection doesn't exist.
Right, but why in this situation? Why with machines? What is it that keeps? So if you did the math and you're like, this is what the answer should be, this is what my mechanical advantage should be, how come it's never going to be what it should be? What's happening? Yeah, well, okay, so what we're looking for is friction. All right, so friction is going to get in the way, and friction is why you can never really have your ideal mechanical advantage. Your ideal mechanical advantage is what you're going to calculate. Okay, so when you have all your data, you have your input force or your distance or whatever data you have, okay, you put that in and you do math, you're coming up with a number. That's your ideal. That's what it should be, all things being perfect. But in the real world, we got friction, right? So friction is going to get involved, and whatever results you get are actually going to be slightly greater or less. What do you think? Do you think your machine is going to have a greater mechanical advantage or a lower mechanical advantage than what is ideal? Lower. Always going to be lower because ideal. So because friction's always present, the actual mechanical advantage of the machine is always less than the ideal mechanical advantage. So we know what we're aiming for ideally, but friction. So if you lived in a vacuum in space, you could maybe get your ideal mechanical advantage, but you'd also not be able to breathe and you'd be dead. So wouldn't matter. Right? Right. So how do we calculate it? All right. The E is always easier to calculate because it depends on locations of forces and distance over which they act. Is this going to be ideal? Oh, the stuff about James Watt, or which stuff?
Types of proteins.
Yeah. Mm-hmm. Yeah, we're going to go over all those. It's going to be cool.
Why was it whited out?
Whited out? Shouldn't have been. Oh, yeah. There was something that was wrong on your, yeah, I went through and fixed it.
The answers instead of the.
Yeah, it did.
Oh, I scratched off.
That's okay. Yeah. For whatever reason that I missed that page when I printed the wrong one. So, all right. So anyway, what's going to be easier to calculate, do you think then? Your ideal advantage or your actual advantage?
Your actual.
Calculating, not observing, calculating.
Your ideal.
Ideal. Yeah. Because calculating your ideal is almost going to be easier, but what you observe is going to be your actual. Okay. So your IMA is what we'll call it, your ideal mechanical advantage. Always going to be easier to calculate because all it depends on is that basic information, right? Your forces, your locations, distance, that stuff. So here's where we come into efficiency. Carlos, was it you that said efficiency?
No.
So, oh, it was somebody over there said it. All right, so efficiency, that's here. That's the percentage of work input that becomes work output. All right, now I want you to think back to our fraction for a minute.
Efficiency equals.
Work output. Yeah. Yeah. So I want you to think back to our fraction 3/4. Okay. We just said efficiency is a percentage of work output and input. What does percentage mean? What does percent? Yeah. That's what it looks like. What's it mean? Did you say? No, not sure. What do you think, Eunice?
It means the number with 100 in the.
Yeah, it's a fraction with 100 on the bottom, right? It basically is out of 100. So if I had 100 cookies and I ate 20 of them, what percentage of the cookies did I eat?
28.
If I had 100 cookies and I ate 20
Okay.
cookies,
80%?
what percent did I eat?
Oh, you ate 20%.
Yeah, and how many did I leave for you?
And you left me.
80%. All right, so think back to your fraction, 3/4. If you did that math, what's the decimal for that? Do you know? Does anybody know?
0.7.
0.75. What's an easy way to remember that? Do you know, did you just know it because you just knew it, or?
Wow.
3 by 4.
Yeah, 3/4. So think about this. Another way to say 3/4. What's another way to say that fraction? 3/4.
3 to 4.
3
2
quarters. You ever heard anybody say 3/4 before?
And
How much is a quarter?
a quarter is it's
25.
there are 4 quarters in a whole.
Yeah, 4 quarters in a whole. A quarter is 25 cents. So $1/4 is 0.25, right? So 3 of them is 0.75.
I've literally never.
All right, so now you've got percent, and you can think of it, money is sometimes an easy way to get to kind of like mentally visualize percent, like try and see it like coins, right? So I'll ask you this one real quick. If I had 30 cents, what percentage of a dollar do I have?
Just give 30%.
30% of a dollar, right?
100 cents in something.
And what does 30% of a dollar look like in coins? How can I see it?
It could potentially be three dimes.
Mhm.
It could be 6 nickels.
Right, lots of ways to do
Lots of
it.
variations.
Right. So the reason I'm bringing up money is because this will be helpful to you when you mess around with percentages and fractions in your head and math. If you can think of money, it's helpful. Like you just said, 6 nickels. What percent of a so a nickel, how many times does a nickel go into a dollar?
Well, it would go in 20 times.
20 times. Okay, so you could say that 5% of a dollar is 5 cents. Right.
One nickel.
Or you could say that
right.
1 by 20 is
So what would be the decimal then for a nickel?
Oh God, I hate
0.25.
Not 25.
0.20.
0.20 because it's 20%, right? Okay, so basically when you see a percentage as a decimal, it's decimal number. And then you move the decimal, right, behind the numbers, and now you have number percent. That's the same thing. 0.25, 25%. 0.33, 33%. Same thing. All right, so efficiency is the percentage of work input that becomes work output. So because there's always some, what did we say?
efficiency.
No, what's always in the way? Because there's always some what? Friction. The efficiency of any machine is always going to be less than
0.
less than 100%. It could be more than 1, but it's less than 100%.
1 though, right? 100% is 1 though.
Yeah, it is. But that's your mechanical advantage, but that's not the same thing as your efficiency. Your efficiency is a percentage, but your mechanical advantage is a number. So it's given as a number.
Oh.
So if you reduce friction, you increase efficiency. That's why a lot of things are greased or lubricated, right? You think about like bushings in a wheel, an axle. Sometimes we have bushings in there and they're greased and lubricated, or you can just put like grease around a wheel if you want to spin with less friction. All right, so here's how you do them. Actual mechanical advantage, like we said, is output over input. So let me hand y'all some paper. Hold up. You already did it?
Yes.
Okay, I'm gonna give y'all some paper in case you need to write. And I'll give you like a minute or two and see if you can come up with the answer to this one. A force of 200 newtons is applied to a machine in order to lift a 1,000 Newton load.
I don't have a pencil.
What's the mechanical advantage of the machine?
Miss Danny?
Yes.
Which is the output force?
So if you're lifting, the machine has to put out 1,000 newtons to move a 1,000 Newton load. So that's going to be your output, right? Your input is what you're putting in. So you're putting in 200 newtons. So in order to lift something, you have to put out 1,000 newtons to lift a 1,000 Newton load. So what do we think is the mechanical advantage of the machine? I'll give you all about a minute or 30 seconds or whatever. See if you can figure it out. And then if somebody wants to offer up the answer. All right, anybody want to bravely offer it up? Eunice?
5.
Okay, so yeah, so what we do is FO. What do you suppose FO means?
Force.
Yeah.
Output.
F sub O is output force. F sub I is input force. So output over input, and we're gonna have 5. Now, it has no units. You don't say 5 newtons or 5 grams per whatever. It's just 5. Mechanical advantage is just 5, 5, 5.
Cancel out the Newton and Newton.
Yep. And what did we do? Yeah, newtons canceled out. Exactly. Boom, boom. So what is this IMA or AMA? Actual or
Actual.
yeah, in this case, so what we're doing here is this is what we calculated. We actually did this one. Like we actually did this problem. All right, so
I love doing.
efficiency.
We have to say you were comparing nanoseconds to like pages. I love doing the
Do you like canceling units? Is that what you're going to
yeah,
say?
I love canceling.
You will like chemistry. There's a lot of canceling units. All right, so if the efficiency of a machine is 40% and it does 120 joules of work, the input of work would be, now what's a joule? It's a unit for work, because remember, joules had to work very hard to mine the joules. So this is going to be work output over work input. So in this case, we know the answer. We know the answer is 40. So now you have to figure out how to get the answer when what you know is the output. How to get the input when you know the output and the answer for the efficiency. Anybody want to bravely give it a shot? Anybody know? Eunice, you want to try it again? What'd you get?
3.
Is it 3? All right, let's look. So what do you suppose W sub O is?
Work output.
Work output,
And work in-
work input, okay.
Is that
And we do times 100 because we're getting a percent, right? Because this is going to be a decimal, it's a fraction. Fractions are decimals, decimals are fractions.
It might be 6 or 8. It might be 6.
So here's how we do it. We put the 40 over here, right? It's a little algebra, put the 40 over here, do the fraction here with the unknown at the bottom. And we're going to turn this 100 to 100 over 1. So it looks like a fraction, right? And then we're going to multiply across and put that 40% on there. See how we did that? See how we moved? When you swap these, see how we swapped the position of these two? Have y'all done math like that before?
Yeah.
Yeah, okay.
It's when you do
300 is our answer. 300 joules, because we need to know work input. So 300. Yep, very good. All right, so let's talk about some simple machines. All righty, so we have 6 types of them. We talked a little bit last week about some. So we have our lever, wheel and axle, inclined plane, wedge, screw, and pulley. Yeah. So inclined planes. This is a ladder. A ladder is a type of inclined plane. So an inclined plane is a slanted surface along which a force moves an object to a different elevation, up or down, usually. The ideal mechanical advantage of an inclined plane is what? Divided by what? Do you know, Carlos? He's finding it. He's finding it. He's looking. He's about that, and I see where he is. He's looking.
It's not there. This page. Right there.
Length of incline over height.
Yeah, it's the distance along the plane and the height. So what you want to do, so if you have like an inclined plane like this, you don't want to measure like here. You want to measure the distance along the plane, which may not be the same as like the length like that. So it's the distance along the plane divided by the change in height, delta height, right? Started at one place and came to another. A lot of these we're going to assume 0 for the beginning, right? It's going to be our final height minus our initial height. Our initial height's going to be 0 in a lot of cases, but there'll be some problems where you're like in the middle of a problem and you're changing things. So then it may not be. So its efficiency is going to be impacted by what? What do you think?
Height.
Yeah. And friction. Yep. All the above. Yep. Definitely. Always friction's always going to be in the way. Friction is going to be a pain. Always going to be in the way.
But it's how you walk.
Right. So here's a inclined plane ideal mechanical advantage problem. So your ideal mechanical advantage of an inclined plane is the distance along the plane divided by the change in height. So what is the mechanical advantage of a ramp of mechanical advantage of a 100-meter long ramp with a height of 10 meters? Darcy, do you know?
Okay, I was about to say 110 meters.
Do we know? So what is it? It's the length, which is 100, divided by the change in height.
Oh, so
Is
it's
it
be
10?
10.
Yeah, look at you guys. All right, so what's RL? R sub L, ramp, length,
Ramp length.
Ramp
Ramp height.
height. There you go. So it's 10. Your ideal mechanical advantage is going to be 10. Now you're going to get in there and why is it then with these are ideal when the one we did about the one involving force and newtons was actual? Because in this case, we're not involving a force, right? There's no force involved here. And because there's no force involved, we don't have to worry about friction at the moment.
Could I go
Right.
get a piece of paper towel?
Yeah, of course. Or the tissue beside you, if you want that. Right there. Yep.
Oh, yes.
So wedges and screws. All right. Wedges and screws are arguably modified inclined planes. Think about it. If an inclined plane is something that changes height, right? Then a screw does change height. It just spirals around a cylinder. But it's basically an inclined plane that's spiraling around. And a wedge is really two inclined planes stuck together, going opposite directions. But really, if we were going to be very specific about simple machines, we could lump wedges and screws underneath inclined planes because they're pretty much just modified ones. So your wedge is your V-shaped object whose sides are two, what did I say they are? It's two what?
Inclined planes.
Two inclined planes stuck together, just squished, right? And they're sloped towards each other. So a thin wedge of a given length has a greater mechanical advantage than a thick wedge of the same. Yeah, if you're trying to, say you're cutting and you have a really sharp knife with a very thin, very thin wedge, right? You're gonna be able to make nice, precise cuts. But if you had a really thick wedge, you're not gonna have those nice, precise cuts, right? Yeah, that's why, does everybody know what a cleaver is?
Yeah.
It's got the big handle, it's a big square blade. It's for chopping bones in half. It's not for making pretty thin, nice little cuts, right? Mm-hmm. Yep.
One time I cut myself with my dad had just, this is actually a few weeks ago, my dad had just sharpened the knives and I was like, oh, I'm gonna make myself, I don't know, something.
Yep.
Maybe an omelet. And then cut my finger right here. It's still
Mhm.
things there.
A sharp blade will cut you really easily, but
Yeah, it was.
you're more likely to cut yourself in the kitchen with a dull blade because you have to use more force because your mechanical advantage is less when your wedge is not as
Fingers
thin.
up like that. I forgot to curl my fingers out like that.
Always curl your fingers. So here's another problem. Mechanical advantage of a wedge is given by the ratio of the length of its slope to its width. So calculate mechanical advantage of a wedge with a thickness of 8 centimeters and a slope the length of 104 centimeters. All right, I'll give you guys a minute, see if you can figure this out.
Okay, so it is ratio length width
Mm-hmm.
0. 124 is
Okay, anybody want to brave an answer? All right, Eunice,
Is it 13?
he's giving a good guess. All right, so
Hold on.
W sub L.
Hold on.
Oh.
16, 32. So
Okay, so there
14.
you go. Okay, look.
14.
So W sub L is the length of your wedge. W sub T is the thickness of your wedge. All right, so 13. Good job.
I did it so fast that I did it so fast that looked like it's 3, but it was actually.
That's what happens,
a 2.
man. So screws again. A screw is what? It's a type of what wrapped around what? I said it a minute ago. Wait, Eunice? Wait, what'd I say? Hang on, you just had it. Yep, inclined plane wrapped around. Think about it. What shape is that? Yes. Okay. Screw is just an inclined plane wrapped around a cylinder. Look at that one right there. Look at his vise or whatever that machine is right there.
This is like not relevant to conversation, but I did a shrinky thing the other day. So
Oh, those are fun. So we aren't going to do any mechanical advantage of screws because they're much more complex problems, but this is how you do it. Okay, so you would determine the circumference of the screw, determine the linear distance that the screw would go if it were twisted one time all the way around. And that's calculated by the pitch in the threads. And then you have to divide that circumference of the screw head by the pitch to calculate mechanical advantage. So screws with heads that are closer together have a greater mechanical advantage. So threads that are close together. So when you have threads in a screw and this, like think about bolts. Bolts tend to have their threads are really close together, but wood screws, they're much further apart, right? Wood screws have like a pointy end, and it's because you're screwing like right into the wood. So you don't have to turn as many times to go as far.
Ages since I figured out the circumference of the screw head. So I think it's like the radius.
Yeah, we're not gonna worry about them. There's how to do it. So if you wanted to do it, there's how to do it. So levers are rigid bars and they move around a fixed point. What do we call the fixed point, Darcy?
A fulcrum.
Yep, fulcrum. All right, so your fulcrum is your fixed point about which your bar rotates. So we talked about this at the very beginning, the distance between the input force and the fulcrum. What do we call that? That distance. Darcy, do you have it?
Distance.
Between the input force and the fulcrum is called the input and fulcrum. Oh, Eunice knows. What is it?
Is it?
It's input arm. Okay, your input arm, or sometimes you'll see it called an effort arm. Okay, how much effort am I using? What's my input? That's between, if you think about you moving like a seesaw, you jumping up and down on a seesaw, it's you and the fulcrum.
It's only fun for
That,
one person on the seesaw.
right? That distance is your input. Okay. And then the distance between the output and the fulcrum is going to be, that's going to be your output arm. Okay. All right. So we have different types of levers. We have 3 classes. Your first one, where's that fulcrum located? Okay, Carlos, do you know?
Between the input force and the output.
Yes, there's your fulcrum is located between your input and output on a first class lever. So first class lever, you can kind of think of it like a teeter totter, or in this case, a pair of pliers is a good example. It's in between, right? All right, now, what's this one gonna be? Second class, Darcy.
The output force is in between the fulcrum and the input.
There you go. Okay, your output force is in between the fulcrum and the input force. Okay, where's your fulcrum in the wheelbarrow here?
Your fulcrum would be
Yep, it's right here on the axle.
the pivot. Oh my
Yep.
goodness.
All right.
It's stupid.
And then your output force, where's your output force?
It's the edge of the handle. Edge of the handle.
Yep, this is your input. You're putting it in here. There's your effort. Right?
Output's in the middle.
Your load is in the middle. So a wheelbarrow, right? Pick up a wheelbarrow. You got your load. Okay, if input is effort, load is output. Okay. So then our last one is alrighty. All right, Darcy, what's this one?
Input force is in between the fulcrum and the output.
Yeah, there you go. So a shovel. All right. So again, you've got your pivot at the end, but you got your effort in the middle and your load on the other end. So in this case, the fulcrum is going to be at the handle. It's in your hand, right? You have the effort. It's near you. So if you look at this guy, here's the pivot. This is the fulcrum. It's in his hand, right? And then this is the effort. This is his input. And then the load is what he's moving down here. All right. So here's an IMA. So a construction worker uses a board and log as a lever to lift a heavy rock. So you imagine how he does that, right? He's got a board, stuff a log, he puts the log on the board, the rock's over here. He's like, okay, I'm going to use this to lift this. All right. So if an input arm is 3 meters and the output arm is 0.75 meters, what's the IMA here? Divide input by output. All right, let's see. All right, LI, lever input, L sub O is lever output. Plug in what we know. 3 divided by 0.75. 4. You divide 3 by 0.75, you'll get 4. How many quarters? How many sets of 3 quarters? How many 75-cent piles? Three quarters can you get into $3? You need to make it into $3. Think about that. It's going to be 4. You'd have 4 stacks. $75 cents, 75 cents, 75 cents, 75 cents. Put it all together, you get $3, right? All right, wheel and axle. A wheel and axle consists of 2 discs or cylinders each with a different radius. Okay, these get pretty complicated too. So to calculate the ideal mechanical advantage of a wheel and axle, you have to divide the radius or diameter. You either do radius for both, the little wheel and the big wheel, the inner wheel and the outer wheel, or you do diameter of both, because radius is half the diameter, right? So dividing radius and radius is the same as dividing diameter and diameter if you're looking for a ratio, right? Like if you have a wheel that's 6 inches across and a wheel that's 4 inches across, you would either be dividing 6 and 4, or if you had the radius, you'd be dividing 3 and 2, but the ratio isn't going to change. The ratio is the same. So what's this one, Eunice? To calculate the ideal mechanical advantage of a wheel and axle, divide the radius or diameter where the input force is exerted by the radius or diameter where the output force is exerted. All right, so these are a little trickier. To calculate the ideal mechanical advantage of a wheel and axle, divide the radius of the wheel by the radius of the axle. So what's the mechanical advantage of a wheel and axle where the wheel has a diameter of 10 centimeters and the axle has a diameter of 2.5? So diameter to diameter is the same as radius to radius because it doesn't change the ratio. And we're looking for a ratio.
Oh, a ratio.
I mean, you need a ratio to get the answer to the problem. So what do you think?
2?
You think it's 2? Okay, so that W sub R
It's 3. It's 3.
and A sub R. So wheel sub radius, axle sub radius. Okay,
I think
5.
2.5. It's 2 or 2.5 or 3. 2.5.
2.5. 5 divided by 2.5. So, oh wait,
Wait, no, it's 10.
that should be, yeah, that should be, hang on. I think let me double check my thing. I'm not stupid. Yeah. Yeah, that's messed up. Yeah, I need to change that. We all looked at it and went, wait a minute, that's not right. Should be 2. There we go. Now we're right. Hold on 2 seconds. I got to fix it for the other group or I will get that wrong for sure. And they'll be like, you got it wrong, because they love to find me wrong. Where did it go? Well, we all kind of caught it together. So
I don't get many brownie points because like I can't spell.
yeah, I can't spell. My problem is that I don't see my own mistakes, but I see everybody else's real quick.
Read a paragraph like
Okay,
4
so-
times. to Make sure.
If you find any, you just write them down. That's all you got to do.
You found all of them. Yeah.
All right, so
One.
moving on. I'm watching our time. So pulleys. Okay. So obviously this is going to be Darcy. Yep. A pulley is a rope that fits into a groove of a wheel and changes the size and direction. Look at that. That's wrong too.
Give yourself a brownie.
I should. I just caught that. I'm like, what?
The lever.
I should say direction. You did? Okay, write it down and put it. Yeah, you can just put it.
FRE.
Yeah.
Ah, you found it though? Then you.
Yeah, me and Lewis found that as well. FRE,
Cool.
it says
Where?
there,
All right,
there.
good. Well, write it down for me so I don't forget it. And just when you're done, stick it over. Whoop, sorry. All right, so the amount of ideal mechanical advantage of a pulley or pulley system is equal to the number of rope sections. This is easy. These are easy. The number of rope sections supporting the load being lifted. So the amount of force required to lift a weight with a pulley is equal to half the actual weight, which means that a single pulley can provide a 2-to-1 mechanical advantage. So you do work over twice the distance you would normally do, and you decrease the force by a half, right? So you also can just make it real easy and count the lines. So this is how you count the lines, all right? So to calculate the mechanical advantage by counting lines, you count the number of rope segments or lines that are either connected to the load or connected to the pulley that will travel at the same speed as the load. So this is what it means by lines. 1, 2, 3. How hard is that? So that means your ratio is 3-to-1. So if you're doing that as a math problem, your mechanical advantage is 3/1 is 3.
Really easy. That is
Really easy. Really easy. Okay.
I know.
So we have different types of pulleys. So what changes the direction of a force? Oh, all right, Eunice.
Fixed pulley.
Fixed pulleys changing the direction. This is like when I told you before, imagine throwing a rope around a tree or throwing a rope over the arm of a branch of a tree, right?
It's basically the most basic one.
Very basic. So what changes the direction and size? Darcy?
It's the movable.
Movable pulleys. So these are the ones that are like in the middle of a line somewhere. Okay, like this guy right here. Got the masses right on it. And then, whoops. And then also, obviously, you've got compound where you put more than one pulley together, and block and tackles. And you're going to kind of create some of these today in lab. But you can see like a compound pulley has a combination of like a fixed and a movable. And then you also have this block and tackle where it actually comes through and back down.
Miss Denny?
Yes, those are used on ships a lot.
Miss Denny?
Uh-huh.
You actually gave us all the answers of pulley and fixed pulley.
Yeah, those are the ones that some people had whited out. I may have missed it on some others,
I
but
scratched
that's okay.
out.
Yeah, that's all right. Yeah, they just
Same house.
issue with printing, but that's okay. So yeah, if you look at the block and tackle, so you pull here, this is going to be raised, right? But it's going to be much easier because every one of these lines is increasing your advantage. So I wanted to end today. This is a little inspiration for you. This is a Rube Goldberg. Okay.
I love making these.
So this is similar to what you guys are going to create at the end of this class. All right. But you